Class, welcome back, students, welcome back to class. This is technically a re-record of a lecture that apparently was missing. I did give this presentation a few weeks ago, but we're recording it so you'll have a copy of it. This is, called Historical Examples of Proportion in Geometry. We're going to be talking about proportion in geometry and really these projects. The Parthenon, we're going to be comparing and contrasting the Parthenon and the Pantheon, and I'm sure you've probably seen this lecture before. But anyway, the Colosseum, Hadrian's Villa, and we're going to look at Hadrian's principal architect, Apollodorus, a brilliant mind and imagination that kind of broke classical conventions in geometry. And then we're going to look at geometry and Baroque architecture, roughly or primarily the work of Francesco Borromini, Rome in the 1650s. So if you want to write these down in your sketchbook, I'll give you a few minutes. But of course, at the end of class, I'll give you time to go back and flip through some of the slides, and you can write some of these down in your books. Of course, I don't have a copy of it after this lecture is recorded. So the last class we talked about before this one is we talked about the golden section ratio. You can proportion a proper ratio of the rectangle using the squares, subdividing the square by half, and letting the compass determine the size of the rectangle for you. And these are some mathematical ratios of the proper dimensions for the golden section. Really, the ratio is 1 to 1.618. The length is really 1.618. We'll talk about that a little bit later. And then we talked about the fact that the Fibonacci spiral uses the golden section proportioning system. Of course, this is a diagram using the system of squares to ultimately draw the golden section rectangle. Let's start with 1, 2, 3, 5 consecutively, add the numbers, you get 8, 13, and 21. So the spiral gets larger much faster than, of course, the Archimedes spiral or other spirals we've seen. Of course, we've seen the geometric golden section in play in the facade of mostly classical architecture. We've looked at Palladian's architecture in Venice, a mixture of what's called pure geometric forms, the cube, the triangle, the circle, the golden section, the sphere. So when you look at early classical or Renaissance facades, they're using the basic geometric forms. You can see this facade is comprised of course, possibly multiple golden sections, the cube, the triangle. The roof pitch in classical architecture is normally 22.5 degrees for the triangle. So if you see the angle of the slope, it's roughly, mostly 99% out of the time is 22.5 degrees. It's a standard angle that classical architects are using. So today we're going to be first looking at the geometry based on the Parthenon and the Pantheon. Now remember from our history lecture, kind of at the beginning of the class, we looked at geometry, structure in space versus Greek structure and Roman structure. Of course, the Greek structure is the Parthenon in ancient Greece on the left, the plan, and then of course the Romans are using arches, domes, and concrete. So they really freed up the space in architecture more so than the Greek architects did. So let's first look at the Parthenon. A lot of people don't know the names of the architects. Of course, there were names, Octinos and Callicrates. This is roughly 440 BC. Here's a wonderful rendering of the temple on top of the Acropolis. You can see the Parthenon is the highest, the tallest building on the hill of the Acropolis. And we've seen that earlier that the golden section rectangle is probably used to determine the outermost perimeter of the facade itself. In this diagram, and of course this one. Now this pitch is not 22.5, it's a little bit shallower. So there's a, I'm just saying that 90% of the time that the angle of the pediment is normally 22.5 degrees, but there are exceptions to that rule. We talked about the floor plan. Let's talk about some geometrical and some other ideas beyond the way the building is constructed in proportions called optical refinement.
Jay, are you sharing your screen?
Oh, I'm sorry?
I can't see your screen.
Oh, hold on just a minute. So you weren't able to see the screen at all?
No, I can see it now, though.
Okay, sorry, I didn't realize it was turned off. Okay, should I start back from the beginning? So did you see this?
No, yeah, that'd be great.
Okay, well, I'll just kind of quickly run through the images first. You know, I mentioned these are some of the buildings we're going to be looking at this afternoon. Here's the way to draw and discover the golden section. We've talked about this before, the Fibonacci spiral. The facades of Palladian architecture using what's called just pure geometric forms, the cube, the triangle, the sphere, and the golden section. Then I mentioned that we're going to be discussing the plan geometry based on the Parthenon and the Pantheon in Rome. Of course, we could see that the space and structure in Greek architecture is very different than Roman architecture because we're using the sphere and we're using masonry and concrete. So the space is really transformed in Roman architecture versus Greek architecture. So here we go. We're going to look at the Parthenon, roughly 440 BC by Actinos and Callicrates. Here's a rendering of the Parthenon on top of the Acropolis, probably the tallest temple at this time, roughly 440 BC. We're going to talk about, we've already mentioned that the facade is roughly fitting into the golden section ratio, which we looked at earlier. But for today's purposes in class, we're going to be discussing the way it's built with what's called optical refinement. So if you look at these two diagrams, the way it's built is, of course, it's perceived on the right. The way it's actually imagined and designed is quite a bit different than the way it's perceived as built. So this is actually how it's built. It's horribly exaggerated just to show the way that they're stylizing the columns as a way of using optical refinement. And what does that mean? So the image A is as intended to be perceived. In other words, they wanted the columns to look straight up and down. Of course, they wanted the rectangular effect facade, but the way it's actually built, they were afraid that if they were to stylize the columns in this manner in B, in other words, they would fear that the building's columns would be tapering downwards. So they deliberately changed that and made the columns sloping upwards to avoid the fact that they didn't want the columns to look crooked in example B. So if you look at the way the columns are actually built, they had to calculate the way the eye would perceive the columns as projecting downward. They wanted to make sure the columns were looking taller and thinner because gradually, if you look at what's called the indices in the columns, they're larger at the base and gradually get smaller at the top. So without factoring that in, they were afraid that people would perceive the columns like this in example B at the bottom. So, you know, this is actually how the columns are built. They're pretty much each column is not exactly the same. In other words, they had to factor in the curved style of base, which is the base the column sit on the entablature, has to be worked to accommodate for avoiding a condition called B. So they took all that into consideration to actually construct the building like this. So pretty much each column is very different. The poor sculptor that had to sort of factor this in and calculate the proper slope and, of course, the column's diameter and the height, the changing curves. It's remarkable that, you know, this many years ago, they factored something as sophisticated as this in. So look at this diagram. The building's columns are actually warped and built like this. Of course, this is what I'm saying, horribly exaggerated just to prove the point, but not all the other temples are built like this. It's just interesting that they went to all the trouble of trying to correct this visual problem. So the entablature is technically curved, but of course this is very exaggerated. You know, if you look at the entablature is technically built like this, but you don't perceive it to be crooked like that. You perceive it to be like this, example A, straight up and down. There's been many archaeologists, architects that have come out and tried to prove this and disprove this, but they were able to measure the columns individually and calculate the fact that this was actually factored into the design of the building. So that's just remarkable that they went to all the trouble of factoring this visual dynamic in. It's hard enough to build a rectilinear building without, you know, power tools, but of course they were so emphatic about having perfection that this was actually considered. So then we're going to look at the Parthenon in Rome. This is really 1st century AD. What I'm saying is Apollodorus was Emperor Hadrian's principal architect. He did extraordinary work, especially his work with, of course, his first building, the Parthenon, which is a temple that is borrowing a Greek temple front superimposed on a Roman dome. So we're borrowing, of course, Romans are borrowing ancient Greek architecture to comprise a new Roman building, which uses the Greek temple front and, of course, the dome behind that. So let's look at the section of, we'll go back to these in a minute. So the geometry of the Parthenon, if you look at the plan, is really these two squares on the left. The entire periphery is, the spaces are designed with two squares, of course, superimposed with the sphere and the circle in the plan. So the entire geometry is a very simple sphere that fits into the body of the actual sanctuary, the nave. So then what happens is the center of the sphere, the circle, is divided in half, which marks the entablature. So the spring line is a horizontal band where the dome projects above that line. So of course the entablature marks the center of the dome. Of course, the curve starts at the top of the cornice and has this incredible concrete dome using coffers. Now the coffers in the Parthenon, I'm sorry, in the Pantheon are not decorative, they are structural. It's a concrete dome, so removing some of the concrete panels in the formwork, that actually makes the dome lighter. So if you look at this section of the dome, it's starting to taper because it gets thicker and heavier as it meets the masonry of the building. So what we're looking at here is the simple curve, the circle, of course, bisected by 45 to determine the placement of the niches in each one of that's carved out of the thick mass of the walls of the structure. Of course, the dome is sitting above that, but there are corridors and voids inside the mass of the wall. So again, we're using optical refinement in the determination of the geometry of the coffers. This is really done to make sure that they are perceived as squares from the center, sitting at the center of the dome. So in other words, in parts, if you walk into parts of the building, some of the domes look rectangular. Of course, if you stand at the center, it looks these are all perceived as all squares. So they had to still calculate the angle of the view to properly perceive these in cross sections. Really sophisticated work to be able to. Now, again, these are wooden forms that are poured into the mold of the dome, of course, removed. And I think this was gilded with either gold or bronze. Of course, during later, they started removing the classical temple front, the marble, the bronze to make other buildings. So this was never an exposed concrete dome. It was probably covered with bronze. But just remarkable engineering to calculate the optical refinement for the coffers and the squares. So here's actually the shell of the structure. The arches are not decorative. They are integrated into parts of the dome. Of course, the concrete is poured on top of there's actually a wooden form that the concrete is poured on top of. But of course, there's brick vaulting inside the dome itself to add lateral structure. Even in the walls, these are not decorative arches, these are the structure of the masonry to relieve the weight of the dome on top of the walls. Again, we've seen earlier is that the exterior would be faced with the Corinthian order in marble. Of course, most of the materials have been removed to make other buildings. But it's an interesting structural dynamic that there is structure inside the concrete. Of course, the brick masonry is not decorative, but there are structural arches inside the shell of the dome. So we're going to get into something a little bit different. The Colosseum, we've seen before, 1st century AD. This is not designed by Apollodorus. I'm not sure the architect of this. But, you know, again, what's happening is the entire facade is made up of nothing but openings and arches. So here's the nomenclature of each one of the arches using the voussoirs, which are the structural curved members, the keystone, which is inserted after the arches are brought up to the center. We've seen this in our earlier diagrams. But the Colosseum's geometry, of course, and plan is an ellipse. We really haven't seen elliptical architecture in classical architecture except for the Colosseum in Rome. This is a functional reason because you probably have more seating on the wider part of the curve versus if it was a pure circle, you have less seating. So of course, the ellipse extends the nave or the stadium to have more seating. If this was a rectilinear form, you would have less, it would be less functional if you're having horse races or chariot races because the curve makes the circulation easier than if you were designing a rectilinear building. So the curve, the ellipse is functional, not really just decorative in this condition. Here is, of course, a reconstruction of the model. This is the reconstruction on the left. The ruin, of course, is as it's perceived now as a ruin due to possibly an earthquake. We look at the plan, of course, it's made up of an ellipse. In our lecture before that, we saw the way ellipses are actually done. You're using focal points or radius points to determine the proper dimension or periphery of the ellipse. You know, we've seen ellipses in architecture in Gothic or medieval. It's called a three-centered arch. To create the curve, you're using two circles side by side. And then, of course, there's really three radius points, what I'm calling the focal points. The one in the center for the curve, the circle, this one, and of course, the larger radius for the larger curve at the end. So what you do is you can create half of the ellipse, flip it over, and have a full elliptical geometry. That's how the plan of the Colosseum is constructed. So possibly the way they were constructing this is they didn't have, you know, enormous circle templates laid out on the side. They were probably using what's called the string method. You would use two large focal points and cross-axis and a longitudinal axis. You would take the string and draw it around to create the curve just using the string of these 2 points. But true ellipses are really derived from conical sections. If you take the sections at diagonals cutting through these objects, then of course you have what's called the elliptical bodies and shapes are drawn for you. But of course, this is not how they would calculate or draw the elliptical plan of the Colosseum. They would be using probably the string method to do this. But if you look at elliptical drawing templates that we use now, and of course on the computer is that they're derived from conical sections. So the computer creates a program that uses the conical sections digitally and of course manually from the circle of the elliptical templates. So it's quite a bit different geometry than we've seen before using the simple square, sphere, and the circle that we've seen in some of the other examples. Well, let's talk about the functionality and the plan of the Colosseum. This is 4 sections in plan: the ground floor, upper floor, the second and first floor. You can see the foundations. Pretty much every single radius point is a circulation zone. We'll talk about and get to that more in depth in just a minute. They're called vomitories. The entire stadium can be emptied in roughly 5 to 10 minutes because, of course, every single quarter has its own staircase, its own corridor, its own hallway. So pretty much the entire facade is nothing but openings. The whole building plan idea is circulation, to get people in as fast as possible, to get people out as fast as possible. So without having every single arch a corridor of circulation, it would take longer for the building to be evacuated. It's a brilliant idea, way to do this. The entire concept is the circulation. And of course, the structure is using the system of structural arches that we've seen. So pretty much the entire periphery are doorways to get people in and out, but they're beautifully articulated with, of course, the classical order. So if you look at the cross-section, there are nothing but circulation stairs, hallways, and corridors, which are very integral into bringing people in and exiting people out after the ceremonies. And of course, the facade which we've seen before is the first layer is Tuscan or Doric, the second layer is Ionic, the top layers are Corinthian. So the simplest order is at the bottom, the more complex they gradually get to the top. Here's a much clearer plan of course, the center of the ellipse are stages with wooden floors. Sometimes they remove the wooden floors and fill it with water to have mock naval battles. But again, the plan is nothing but a radial centrical plan of corridors and hallways. So we're going to move on to Hadrian's Villa. This is another project by Apollodorus. This is probably Hadrian's most elaborate complex of architectural, what I'm calling treasures, geometric explorations. It's a celebration of complex convex and concave forms, which we really haven't seen in classical architecture. What we're going to see is kind of a precursor into Baroque architecture. But Apollodorus was probably such a clever architect, he's able to sort of mix these forms in a very sophisticated and playful manner. This, of course, is after the construction of the Pantheon in Rome by Apollodorus. Let's take a look at the master plan of Hadrian's Villa. This is a huge complex of a myriad of different buildings. Some of these are stadiums, some of them are reflecting pools, some of them are private villas. If you can see my drawing table, I'm going to draw a geometrical relationship looking at, see the large body of space, the rectangular. Can you see my cursor? Okay, we're going to look at the collision between rectangle A, the round knuckle that resolves geometry between A and what's called J, the large canopy surface center. Before we get to that, we're going to be focusing on the cylindrical space here, which of course is called the Maritime Museum. Here's a large model that's actually there at Hadrian's Villa, because the villa is now ruined in most of the museum. Here's the famous canopus you've seen. If you go out there, the postcard features the famous canopus, which is actually reconstructed here. It's a large, enormous reflecting pool. Here's a plan of it. I think it's probably 150 meters long. This is just an enormous reflecting pool. These really intriguing apses and exedras at the terminus at the end. Before I show you that, let's kind of look at just some basic geometric shapes that are found throughout the villa. Apollodorus is mixing convex and concave curves in a very playful language. Especially some of these buildings are really unprecedented levels of geometry we haven't seen before. It's interesting he's mixing the curved bodies as concave and concave forms. If you look at, we're going to be looking at Baroque architecture later. So it's kind of mixing the elliptical geometry with the curves. So it's kind of a precursor to Baroque geometry using the complex and concave forms. Here's another really incredible plan of those curves. So we're going to focus on the Maritime Museum by Hadrian's Villa. Here's a plan just singularly by itself. Here's a plan in the context, which we're going to draw and look at in just a minute. Here is a reconstruction image of the outside of it. Of course, it's just a round cylindrical body with some very complex curves. Here it is now seen as a ruin. We can still see the floor plan just barely in parts of the fragments. So let's go back up and look at the Maritime Museum, which of course this curved body, which resolved the geometry of these two larger spaces. So let's look at my drawing table for a minute. So the way it looks like these are arbitrarily all placed together, there's a very specific geometric relationship about the way these things are ordered and placed. I'm just going to draw the large space here. So the Maritime Museum is a small little independent villa that resolves the geometry between these two angular parts. This is a large open gallery. This is a large open gallery. So let's take a look at the way these things are positioned. So we're going to take the corner of this rectangular body, draw the angle from one corner to another. Then, of course, it determines the center of the Maritime Museum. Can you guys see this on my drawing table? Some of you guys are participating. Hopefully you can. Then, of course, the angle from the two corners goes through the center and determines the placement of the corner of this rectilinear body here. So what looks like, if you look at it on the screen, it looks like an arbitrarily determined placement of these things. There's a very emphatic strategy of line the way these things are positioned on the site. Now, a lot of these things are angled based on the topography. So you don't have a 200-foot tall retaining wall. So a lot of these are angled to maximize the topography. So that way you don't have a large space that projects out perpendicular to the hillside. So it looks like a plan of arbitrariness, but it's a very careful layout of strategy of lines, regulating lines, and of course the layout of the topography. But the geometry of this is very complex. It's a mixture of the number 26, the center is a large reflecting pool. Then of course there's bedrooms. It's a little small independent villa that has bedrooms, bathing facilities, pretty much centered around a large moat of water. So this is quite a bit elaborate than some of the basic Greek and Roman topologies in geometry we've seen before. Not only that, if you look at the plan, you would have to construct the curved entablature of the foundation, and of course the columns to accommodate for this. So Polydorus's work in geometry is very original compared to what we've seen before. Difficult to draw and difficult to construct, but yields some really wonderful results. Okay, so now we're going to transition into Baroque geometry. What is Baroque geometry? Roughly 16 to 1700, right before neoclassical. The word Baroque means irregularly shaped pearl. The proportions are warped. The geometry is compounded and complex and primarily elliptical. We're going to talk about the geometry and, of course, the experience of these places, pretty much seen in these two buildings, St. Carlo and St. Ivo, both by Borromini, both in Rome. So the plan is a very dramatic contrast to what we've seen earlier, is that, of course, Borromini in this example in St. Carlo uses overlapping ellipses, even very difficult, very complex to imagine, draw, and of course to build. The same thing with the one on the right, St. Ivo. So here's St. Carlo, Quattrofontaine, the Church of the Four Fountains, 1650 in Rome. These are the facades. What I'm saying about Baroque geometry is the facades are not planar elements, they're warped. The facades literally are displaying the convex and concave forms. And it just yields some really unbelievable undulating walls. Imagine being a stone carver and carving these things out. You'd have to have a master craftsman to be able to pull these off. There's a mixture of the exterior facades and, of course, the interior images. Sorry, this slide is not as clear as I'd like it to be. But here's a plan of the geometry. What's happening is we're looking at the focal points, the radius where all the curves are created. And then, of course, the axes are started at the focal points and go back and determine the placement of these side altars. So it looks like a very crazy plan of curves and ellipses, but there's a very specific way the geometry is created in this. You know, the digital geometry is using warped and elliptical bodies to determine the form, but I always go back to Baroque architecture and geometry because these are manually constructed with tools, compasses, and other drawing systems. It's easy for students to design, you know, elliptical building, not really understanding how these things are actually created manually. So for somebody to draw this, imagine this, draw this, and convey this to a lay person to build this, it's just extraordinary feat in architecture. And of course, it has these wonderful thick walls which resolve the geometry between the two thick walls and, of course, all the spaces. Here's a wonderful cross section. The thickness of the wall is really incredible. It's not just one planar element. There's undulating curves that are carved. It looks like somebody took a large piece of stone or marble and just carved out the spaces. So part of the experience in this building is it looks like you're walking through a large cloud. It's all painted white. It's a mixture of plaster and wood. It's, of course, since it's a church, it's looking like you're walking into heaven. It has this extraordinary experience, like walking through, you know, Gothic cathedrals. The experience is just absolutely unbelievable. But in these small churches, they're relatively small compared to the cathedrals around Rome. But it looks like you're walking through this large, exquisite cloud. Of course, we have this extraordinary hand by Borromini to create and draw these things. Even the fact that the coffers are so complexly drawn, that's not a word, but the coffers are so complex, it would be difficult to draw those if you're not an experienced draftsman. So now we're going to look at St. Ivo. I'm sorry, some of these images are not that clear, but St. Ivo, there's some other images of St. Carlo. St. Ivo is another smaller church by Borromini. Oh, again, this is what I was showing you. This is Mario Botta's cross-section model that's actually built out of wood. What he does, this was actually built as a temporary installation on Lake Como in Italy. He built the cross-section of the entire church of St. Carlo. So these are individual little pieces of wood that are cut on a laser and then assembled with little spaces in between each piece of the wood. But again, you can see that the coffers and the interior spaces are carved on a large cross section. The first time we've actually seen the full cross section of a church like that. I just thought that was an incredible construction to build just the cross section of this church. So the last we're going to look at is St. Ivo in Rome, of course, by Borromini, roughly the same year. Let's look at the geometry in the plan. It's a mixture of triangles and circles, not ellipses. And it's a very symbolic geometry. The triangle is, the Father, Son, and Holy Ghost. It's a very appropriate geometry, of course, for a small church. And these churches are relatively small. Here's a plan of it. It's interesting that there's really no consecutive continual planar elements, except, of course, are the walls, which are the adjacent context. But it looks like somebody took a large block of stone or marble and chiseled out the spaces. Here's a large plan of the church, of course, with the courtyard. We look at geometry. Probably there would be 2 squares that would fit into the courtyard. So probably 1 square here, 1 square here, and then another larger square for the periphery of the chapel. There's a wonderful view of the courtyard, of course, with the exterior of the church. Again, we're looking at the undulating wall, which is a careful construction of convex and concave curves. It's interesting that Borromini mixes classical architecture with the paired Corinthian columns and, of course, the spiral at the top. Very whimsical way to do a spiral or a lantern on the church. Especially the way the facades are layered. There's not just one opening, but there's consecutive curved arches that layer the walls around the windows. Here's an incredible cross section. Of course, these are all painted white. There's a wonderful term in architecture, it's called poché. It's a French term. It means pocket. But I was saying earlier, it looks like the building has been carved out of a solid block. The thick walls intensify the spatial definition and experience. So we talk about poché. These are excellent examples of poché, because look how thick and sculptural the walls are. I think this is Borromini's own drawing. This is an early scheme. Of course, the final scheme has these beautiful, and look at the ceiling. I mean, the floor, of course, it's a heavenly body. It's like you're walking into a large cloud. But Borromini mixes and changes up the classical architecture. You can see the frieze is carved on the curved part of the entablature. The entablature is now curved with an exaggeration or stylized motif of the triglyphs and the metapiece. Now, the windows are deliberately drawn as built as tapering to make them look taller than they actually are. So Borromini is using optical refinement in, of course, the windows on the church. And these are stunning photographs of just the entire thing painted off white. This is the last slide. I didn't include this in the earlier lecture, but this is ancient Rome in the 1st century AD. We've seen kind of a beginning delve into complex geometry. For the most part, we do see the pure semicircular curves, but we do see kind of a blend of the large coloidarium number 14, the curved exedra beautifully transitions the other spaces around the post-shaped parts. But for the most part, we're still using pure geometric rectangles and curves. Definitely a less sophisticated plan geometry than we've seen in Apollodorus' Hadrian's Villa. That's actually my last slide. I was going to go back up to the first images. And for the students that are in class, I can stop at one of the slides if you're interested. You can ask questions. I think there's 4 or 5 people. You're more than welcome to ask questions or comments, or I can go back to some of the images for you to look at. It's really important to assess architecture in pure geometric languages. Yes, did somebody have a question?
Jay, I don't see any questions in the chat.
Okay.
Was this review from the first class or the second or both? I can't remember what you said.
Well, yeah, again, we're recording this lecture, but there's actually, what I did was I went back to one of our first lectures in geometry. We talked about the golden section.
Got it. Okay, so you put them together in one?
Yes, so really this is historical examples of proportion in geometry specifically, because this chapter is proportion and geometry. This lecture is specifically historical examples of proportion
Awesome.
geometry showing these examples, the Parthenon,
Yep.
and the Colosseum and Hadrian's Villa and Baroque architecture.
Got it. Just wanted to check. I think I missed that in the beginning. That's all. Thank
Okay.
you.
You know, it's also really important to know the distinct difference between Greek space and Roman space. You would never have a Greek space with a circular plan and a dome at all. It's also amazing to think that I'm calling primitive sculptors could, you know, imagine and create this, you know, distorted view and actually build that. Now look how simple the geometry of this extraordinary complex building is. And it's just a square and a circle. Now, if you look at this cross section, the way these are designed and perceived, probably they lay these out in person. You know, probably the draftsman was standing here at the center and projecting lines up to actually perceive that the coppers as actual squares when they're actually built, you know, more warped and rectangular. You know, when I was a student in urban design class, when I first got this map my professor sent me, I thought it just looked like a very complex, undesigned, arbitrarily placement of all these buildings. When you start graphically, geometrically analyzing the position, there's a very specific way these things are, excuse me, oriented. And of course, Apollodorus probably had a lot of wine to drink before he was creating these unbelievable plans. I mean, who would have thought to break the entablature with a curve and then have a large curve above that?
Jay, do you want to show us how some of the buildings lay out?
Yeah, I did. I did a quick example on my drawing table. Did you see that?
Yeah, I can see that. I just, if you have any more like examples of how those are related.
Yeah, let me expand on. Can you guys see the drawing table again?
Yes.
Okay, so let's take a look at, this is the famous wall at Hadrian's Villa is roughly here. Let's take a look at the placement of the canopus. Can you see the cursor on my screen? Can you see the cursor moving around?
Yes.
Okay, so the canopus that we saw here earlier is a long, linear elements. this one, and how does it positioned in that large arbitrarily looking field? So here's the end of the canopus here. This is a plan drawing as it exists now as a ruin. But let's take a look at the center of this. Now there's a large angle. The center of the canopus is derived from the center of this body, which intersects the large diagonal. So then you can cast that up as the position for the canopus. Here's the end of the canopus, which we've seen before. So the entire thing is oriented at there's a wonderful little portal at the end of that. So when you stand here, you can see the entire vista all the way through. You can see, of course, those columns that march along the reflecting pool. And of course, the rectilinear body that goes out to here is, of course, perpendicular to this, the central axis, which of course then determines the center of the rectangle. So if you look at the cursor on my screen, let's go back to, I'm not sure what this body, this large, it's an outdoor enormous courtyard. Look at the center of this here, then of course it probably goes to the very center of this space called A. Oh, sorry. So if I were to continue this angle up, it would probably determine the center of another space here. Then of course the pochette is the mass that resolves the geometry between the two geometric parts. So if you look at my cursor again, let's take a look at the Maritime Museum and plan. If I were to continue, well, my sketch isn't really that successful. If you were to continue the center of this, then probably the center of this is determined, goes to the center of this rectilinear reflecting pool. So pretty much there's an enormous strategy of centers on this. You know, I'd have to trace over the actual image, but it's hard to tell if the center spans from the actual center here or from the center here. You'd have to just kind of analyze that, because it looks like the center of the canopus is actually from the center of this main courtyard here and actually spins off like that. Did that answer your question? Or?
Yes, thank you.
Okay, Jay, there is a question in the chat that says, in Hadrian's Villa, are the sight lines preserved between the buildings as you've drawn them, or is it mainly a theoretical arrangement?
That's an excellent question. It's really a theoretical arrangement, because when you experience the place, I'm not sure you really can't experience those alignments, but there are places where there's windows and portals that do give you clues about the alignment of things. Like I was showing you, I think like there's probably a large portal or openings in some of the walls. You can see that strategy, but you can't really see the way the plan is laid out when you walk through there. It's really hard to experience that in person. That's a good question. Yeah. I mean, for any architecture, landscape architect, if you're doing, this is the perfect model for doing a large complex of a hilly site. Because if this site were flat, let's take a look at, go back. This doesn't quite show the hillside very much, but if it were completely flat, that would be a very different plan organization, because probably the way that this is positioned, especially this one, if you were to turn this large courtyard perpendicularly to the site, then the retaining wall would be enormous. So by orienting these, you're kind of reducing the height of the wall so they don't project out above the slope so far. Yeah, I just would put the Maritime Museum as a special little hidden gem. It's unfortunate that, we can't experience it now. It's seen mostly as a ruin. Okay, and then I think we have a few more minutes for some other questions.
Okay, so there's another comment or question in the chat, also from Eric Fisher, that says, so if the alignments are mainly conceptual, it makes me wonder how much of classicism relies on the conceptual arrangements and how much is intended to be visually perceived. Can you talk about the difference between these?
I mean, architecture is a specific order to things. I think architecture is space, form, light, and order. It's interesting. It's kind of a hard question to answer, but I think the thing is, if you can't visually see the strategy, then why even do it? I've often wondered that myself too. But there are places where you can experience these plan relationships in parts. I mean, you can't, like in Hadrian's Villa, you can't possibly comprehend the whole site strategy walking through there. It's very complex. But even if you can't see the relationship, then you can experience some sort of order to things. Especially, it's easier to see order in, of course, the plan of these early buildings, because it's a very simple circular plan. Did that kind of answer your question, or you might want to elaborate on your question in case I missed something? But if you look at the site, the large site plan, a plan of Rome, the Noli map, there's no order to it. It's a very chaotic, irregular geometry. The streets are all crooked. It was only until Pope Sixtus V implemented his obelisk plan to maybe straighten some of the streets out, to at least have an order to orient yourself in the city. You can definitely see those. but it is difficult to see, well, especially in a planned order, the intended geometry. But then, of course, you can clearly see order and geometry visibly, especially on facades. Like, let me go back to this one. Like, if you weren't using any proportional relationships on, hold on, let me go back. Look,
So he responded and said that was great, thanks.
Yeah, because facades are easier to see the geometric and strategized relationships because it's, you know, one plane, but it's really hard to experience the centering devices in when you're actually walking through there in person. Yeah, that's an interesting question. But if you didn't use those in plans or sites, then even imagine how chaotic a plan organization would actually be. Okay, so on April the 13th, our next lecture, it's a different chapter. We're going to be talking about literature and selected paradigms of writing and theory. We're going to be talking about specifically Vitruvian's books, the 4 books of architecture, Shepherd and Jellicoe's landscape architecture books, and some other important journals. So we're going to be taking a break from geometry and proportion and delving into kind of a short introduction to literature. Should be pretty interesting. Then, you know, how do you take words and ideology and actually draw that and build that? So the next chapter, I think 5 or 6 classes will be more theory than geometry and proportions. And I'm sure there'll be a lot of questions. And hopefully these lectures are enhancing your understanding and experience of architecture. You know, I have to kind of factor in that a lot of the students in the class are kind of novices at architecture, design, and composition. But of course, there's many other practicing architects that have probably learned this before. It's good to have kind of a refresher of things. And of course, there's not one person in the world that knows everything about every historical or architectural topic. Again, I'm coming from this as a designer, not really a historian. So. But when I look at these, it makes me want to draw something. I mean, if these don't get you excited about building something, you're probably in the wrong business. Okay, Michelle, I think we have 5 more minutes. Are there any other questions?
I don't see any other questions. I think we can probably have this be our stopping point.
Okay. Okay, thanks, Michelle. Thanks everyone for attending.
Thank you, everybody. Bye.